All right, good morning, everyone. We're going to be starting our volume section on this method. We're going to split up volume into three lessons: this method, washer method, and cross-section. So this method and washer method are very similar. We'll spend today going over this method. Tomorrow, we'll probably spend more time reviewing this method and probably circle back to some area formula or area problems that we didn't get to do on the back sheet of that worksheet from yesterday. We just did that first page. And then Thursday, we can talk about this washer method, which is going to extend this concept to where there's a gap or a hole in our object. Okay. But first, I'm going to start off by just doing an area problem as a way of review, but more importantly, for us to have something to compare and contrast with area and volume to see the similarities, but then also some distinct differences that we're going to have to be aware of. So, but they're very much connected. Our area really is a building block for what we're going to be doing with volume using this method. So recall finding area under the curve of y equals square root of x. So this is my square root of x graph here. And the understood other function is this horizontal line, this x-axis, which we know is y equals 0. Okay. Between regions of 0 and 4, I'm just going to mark it. Yeah, not very accurate here, but. So let's say 1, 2, 3, 4. And we're just going to shade in that region. And we're going to be finding the area of this shaded region here. Okay. Now we're dealing with functions, and we see that there's this vertical component, top minus bottom, that we can do with our rectangles. So we're going to go ahead and draw our representative rectangle that connects one boundary to the next. So we can imagine these are infinitely thin rectangles, infinitely thin, infinitely many to the left and to the right of the representative one that I drew, but they're all going to be vertical. They're all going to be stacked from one end to the other end in this orientation. Okay. Now, if we imagine all these infinite numbers of rectangles, the tops of every rectangle is hitting the same graph every time, so there's consistency there. If we imagine infinite numbers of rectangles, they're all hitting the same bottom graph, so there's consistency there as well. All we need is one formula to find the area. So let's go ahead and do that. Our area is just going to be the definite integral from one boundary to the next. So from left to right, in this case, in terms of x, from 0 to 4. Top minus bottom. So the top of the rectangle is hitting the root x. The bottom of the rectangle is hitting the 0, is touching that y equals 0. So we say root x minus 0. And then we finish it off with dx. There is a height and width component that we have here. So this root x minus 0 is that distance, that vertical distance, which will represent the height of one of the rectangles. And then dx represents the fact that we're finding the integral with respect to x, but it also kind of has that component of the width. So height times width, we accumulate that from one boundary to the next, and we have infinite numbers of rectangles, areas of rectangles, because height and width produces what we know to be area of rectangles. Okay. So I want to just bring that component up, and we're going to see how it's going to be a little bit different with volume. But let's go ahead and finish this problem here. We can do calculator, but I think this is easy enough. We're going to do this by hand. We know square root of x is x to the 1/2. We can push it through a power rule, make it x to the 3/2 over 3/2, right? Add 1 to the exponent divided by that new exponent. Push that 3/2 up as 2/3. And then evaluate your bounds from 0 to 4, but you're always evaluating the top first. Okay, the 0 goes away. You can work this out by hand. Square root of 4 is 2. 2 cubed is 8. 8 times 2/3 is 16 over 3. Or use your calculator. But essentially, we have area being 16 over 3, and we say unit squared because it's a two-dimensional unit. Okay, so did this problem so that we can have something to compare with and look at the similarities and distinctions when we move from area to volume. Now, let's move on to this shader region. So this is the same shader region as above, but now let's imagine this. We're going to take the shader region. This is a two-dimensional shader region here, and we're going to rotate this around the x-axis. Okay, so we're going to indicate that we're rotating around the x-axis. Use a dotted line to indicate that the idea of rotation. And we're going to rotate it. We're going to call this the axis of revolution. Which I'm going to abbreviate as AOR. Now, if we rotate this 360 degrees around this axis, imagine this is now the center of the object, right? If you're rotating something around that line, it's all of a sudden going to be the center. And imagine if you can visualize what's going to come out of it. It's going to be these bowl-shaped objects, right? This bowl-shaped object, but it's all of a sudden going to turn into a three-dimensional, visually a three-dimensional object that you can imagine holding in your hand. But instead of, we can think of this object as an accumulation of not rectangles, but of these circular discs, these really thin circular discs. They all have different heights, and they all are going to help accumulate the volume of this object. Okay. We're not going to have to be able to draw these. We're just going to have to be able to pull the information that we need to get to the volume formula. But I want to just point out certain things as we go through it. We're still going to draw this distance from the axis of revolution to the boundary. And it's going to look a lot like the rectangle that we drew above. We're still going to do the same thing. We're still going to do top minus bottom. But this is going to represent something different. Do you know what this now is going to represent?
It's going to represent the radius.
Good. Radius of these circular discs. So we're going to call it now the radius, even though we're drawing it very much the same way as how we do rectangles. But because of the fact that we're rotating and we're putting into a different formula, it's now going to represent something a little bit different. And yes, this is now going to be representative radius of these circular discs that we're accumulating from one end to the other. And we usually call it big R of x. Okay. And the reason why we have uppercase R is because later on, we're going to have a little radius that we're going to see on Thursday, where we're going to have to need to subtract out a gap or a hole in the object, and for ring-shaped figures and ring-shaped objects, and that's where little r is going to come into play. But for now, all we're using is a radius called big R. So let's just look at one representative cylindrical disk. Okay. Now, we know that there's going to be that radius component, big R of x. But because we're rotating 360 degrees, there's going to be a circular aspect of our shape, right? These are going to be circular disks. So we're going to have to involve area of a circle for the face of one of these disks. So area, we know, is pi r squared. But we have a certain name for radius. This representative radius is now going to be big R of x. And we're leaving it as a function because we wanted to give it that flexibility to adapt to the changing heights of all these radius. So now our area is pi big R of x quantity squared. So this is now going to represent the face of one of these circular cylindrical disks. And now we can start putting this into a volume formula. Okay, so here's the volume formula, V equals. Okay. We're still going to have the integral. We're still going to be extending from one boundary to the next, from x1 to x2. But we have a slightly different shape, right? We're no longer dealing with rectangles. Now we're dealing with these cylindrical circular disks. And part of it is going to be involving the area of a circle. So we're going to have to involve area of a circle. So pi big R of x squared. But then there's also going to be a width component to give it that depth, right? To give it that third dimension. And that's going to be a dx. So you think of that dx as a representative width, just like how dx is a representative width of our rectangle. Now look at the component here. Pi r squared is area, right? That's already a two-dimensional calculation. But then we're going to add on this dx width, which is a third component, and that gives us our third dimension, right? Area, we plug r of x into the area formula, and then gives us that two dimension, and we add that third dimension. So look at that distinction here, right? Area is only width and height, but then volume is going to be area times width, gives us that third dimension. Okay. So similarities in the fact that we're going to be treating radius the same way that we do height, but then we're just inserting into a different formula and we're calling it something a little different. Now, typically, we like to treat this pi as a coefficient. So I put it inside just to help us see that it's pi r squared, it's the area, circle area formula. But as we do our formula, we like to push that pi out in front. So V is equal to pi integral from x1 to x2, and then big R of x squared. So typically, if it's a coefficient that we know is not changing over the entire course of the problem, we just like to push it out in front, and eventually we're just going to attach it to the end of our answer. Now this form that I have also on the formula here in the middle of the page, just like how we have different orientations for area, top minus bottom and right minus left, we're also going to have different orientations for volume. So this is the orientation for top minus bottom. Everything is in terms of x. We're going to do a couple of problems exploring this form first. R of x has to be in the form of y equals. So a lot of these similarities that we've explored with area, it's going to just carry down. We just have a slight adjustment with the formula that we're inserting in, but everything for the most part, we're carrying a lot of our area information down to our volume as well. Okay, so I went over a brief overview using this as an example to show where the formula is coming from. And now we're going to go back and actually find the volume of this particular object. Right? So same scenario as the area problem, but now we're going to make this into a volume problem. Okay, so example 1, same scenario as above. We have y equals square root of x, rotating from 0 to 4. We have that same shaded region, but now we're going to be rotating it. Okay. All right, so I want you to do this here. We're going to be rotating around the x-axis. So whenever you see the word around, you know that they're about to tell you where the axis of revolution is. Around the x-axis. So that's y equals 0, right? So I want you to get into the habit of drawing your axis of revolution as a dotted line. That way it kind of gives you a visual reminder where the center of your object is going to be located. So I like to draw a little circle with an arrow to indicate that we're spinning that shaded region around that axis. Okay. Now, something to keep in mind is that your radius is always going to be perpendicular to your axis of revolution. So if your axis is horizontal, your radius is going to be vertical. Okay. If your axis is vertical, then your radius is always going to be horizontal. Okay. So we're going to draw the radius now. Now, I want us to draw the radius a very specific way. It doesn't seem like a big deal now, but it's going to be really important to help avoid mistakes, especially when we get to washer method. So the way I want you to draw the radius is I want you to start on the dotted line. Start at the center of your object. This is the true center, because once this is rotated, there's going to be a portion that's below to create the bottom part of the bowl. So start on the axis, and you're going to extend to the boundary of the shaded region. And it should produce a perpendicular orientation from your axis of revolution. Okay. I know it doesn't seem like a big deal because that's the only way you can draw it right now, but I'm going to keep reminding us, start on the axis. And if you already start on the axis, we're going to allow us to prevent some issues that a lot of students run into. Okay. Now, that vertical radius is also a good reminder that we're dealing with top minus bottom. We're going to put it into this form, and we're going to insert everything into this formula here. Okay, so that's a good visual reminder that we're dealing with the top minus bottom formula. So we know if we do top minus bottom, our equations have to be in terms of y equals, and just like before, everything is set up for us to do that. So we don't have to rewrite the equation. Everything is set up for top minus bottom. Okay, so now let's build our radius. Our radius is just the top of the radius minus the bottom of the radius, so big R of x. We see the top of the radius is touching the curve, so root x, minus the bottom of the radius is sitting at 0, so minus 0. Cleans up nicely to just be root x, so we say R of x is just root x. We have the bounds visible to us. I think we're ready to put into our volume formula. So V equals, start with the pi. We typically like to put the pi outside the notation. Okay. And what are the bounds going to be from x1 to x2?
0 to 4.
Yeah, left to right, pretty obvious. All right, so now we have to make sure that we put our radius down, but we make sure that we square it. Okay, if you don't square your radius, then you're not truly representing the circular portion that's coming out of the shape, right? So we have to make sure we square our radius. So our radius is root x, quantity squared. Okay, Next page, we're going to be dealing with more complex problems where we can use our calculator, but I think it's easy enough for this one for us to just work this out by hand. So if I clean this up, 0 to 4 of x dx, easy power rule here, x becomes x squared over 2. Now we can work in the bounds. Upper bound always gets plugged in first, so 4 squared over 2 minus, followed by the 0 squared over 2. 16 over 2 is 8. 8 minus 0 is 8. And what do we have to include as well? We don't want to forget about pi. Yeah, pi is part of our area formula for circles, so we have to make sure that's part of our answer. It's not going to go in the calculator, but that way we can achieve exact value. So we can put in the calculator, but we prefer exact values, so we typically just leave it out the calculator and then we insert it manually at the end. Okay. We include units cubed because now it's a three-dimensional value because it's volume rather than two-dimensional for area. Okay, any questions so far? Okay, I'm laying the some of the foundations of what we're going to see later on, but I just want to point something out here. Look at that dotted line, okay, and look at that shaded region. Do you see how that dotted line is right up against that shaded region that you don't see any gap or any hole? There's no partial gap, there's no hole. So that's an indication that we're using the right formula. I know we haven't talked about the other one yet, but I just want to point that out. This method, we know it's this method when your dotted line is right up against the flat surface of the shaded region. So if it's up against the curved region or if it's only partially touching, then we have something else for it that we're going to see on Thursday. But here, this indicates that there's no gap. We don't have to subtract anything out. All we need is one radius, and that will handle our problem. Okay. All right, let's go to the back page. Okay. Find the volume of the solid created by the function y equals 2 minus x squared. I forgot to include this as well. And y equals 1. So we have two equations that we're going to be looking for that shaded region, but then it says around the line y equals 1. So this is meant to tell us where the axis of revolution is. Okay, so let's start off by graphing our two, so we can get our two graphs so we can get a visual as to what we're working with. So I have y is equal to 2 minus x squared. If you think about 2 minus x squared, that's the same thing as negative x squared plus 2. And really, negative x squared plus 2 is just a parabola that, negative x squared is a parabola that opens down that goes through 0, 0, right? And then the plus 2, it's just going to take that negative x squared and it's going to shift it up 2 units. So that's what we're going to draw. We're going to draw a parabola that opens down with a vertex with a y-intercept at 2. So here's my graph. Negative x squared plus 2. Move it up 2 units. We also have the line y equals 1, so that's going to be a horizontal line. And you see how there's a enclosed region that we can shade in. So we're going to be working with this shaded region here. Okay. Axis of revolution is y equals 1, so I'm going to put a dotted line right at 1. Okay, so notice again that dotted line is right up against the flat surface of the shaded region. This will be a disk method problem. Now, next step, we're going to draw the radius. We know the radius is going to be perpendicular to our axis of revolution. start on the dotted line. That's the center. You always want to start at the center of your object, and we're going to extend to the boundary of our shaded region. So extend to the boundary here. All right, it's a vertical radius, which means that our formula that we're going to be using is going to be a top minus bottom. Everything's in terms of x. Our formula is going to take on the form of y equals. And it looks like everything is set up perfectly for that situation. Okay, so what's the top of the radius touching? Okay, what's the bottom of the radius touching? Good, y equals 1. Right. So having that radius drawn is very, very helpful because we can visually see exactly what we're dealing with. We're going to see more and more distractions later on, and having those radius drawn, we can identify exactly what is needed to create that distance between the top and bottom. Okay, so let's build our radius. Okay, top minus bottom. The top of the radius is sitting at the 2 minus x squared, so we start there. Minus the bottom of the radius, which is at 1. I like to put a parentheses there, so I don't. That's a good habit there. Clean that expression up. That cleans it to be just 1 minus x squared. Okay, so we have something that we can insert into our formula, but we're still missing what?
Bounds.
We're missing the bounds, right? And how can we find the bounds?
Set the y equals 1 equal to, like, that's the y value.
Sorry, say it again.
Like y equals 1 would just be substituted with f of x, like f of x substituted with 1.
Right, so we're just setting the two equations equal to each other. We know that visually the intersection of the graph and the horizontal line is going to tell us where the boundary is. Yeah, so to find the bounds, okay, we'll set equations equal. So I'll say 1 is equal to 2 minus x squared. I'll bring the x squared over to the left. I'll subtract 1 to the other side. So x squared equals 2 minus 1, which is 1. Take the square root, and I'm left with what? Good. Plus and minus 1. So those are my two boundaries showing up right there for us. Okay, I think we're now ready to insert everything into our volume formula. So V equals, let's start with the pi integral from -1 to 1. That's what we found here, right? -1 to 1. Make sure you square your radius. So we're going to put bracket 1 minus x squared, quantity squared. If you don't square your radius overall, you're losing that circle component of your formula. And I mean, we could do this by hand. We could FOIL this out, but let's just practice entering this into our calculator. So I'll show the 36 Pro first, and I'll move on to the 84. Okay, don't enter pi into the calculator because we want to achieve exact value. So we'll start with the integral. We're going to go from -1 to 1. Parentheses, 1 minus x squared. Close parentheses, and then we're going to square the expression. Okay, hit enter. If you get a decimal value, see if you can convert it into a fractional value. Sometimes it may not be able to, but we can always try. So there's that fraction to decimal button or decimal to fraction button. It does, so we'll prefer this answer. But if it doesn't, because it's not able to convert, then you can write it to 3. You can represent your approximation to 3 decimal places. Okay, and what do we need to include as part of our volume? Pi. 3-dimensional solution here, a 3-dimensional calculation, so units cubed. All right, I want to show it on the 84 as well. Now, this is what I like to do with the graphing calculator. Down the line, our expression will become more and more difficult to manage. Just becomes messier. And with messy expressions means more parentheses to make sure that we don't lose track of order of operations. And what I like to do is I like to try to avoid all those parentheses. So the way I like to do that is I like to have my radius held in a different location. I like to have my radius held under y1. That way it is just a lot cleaner. And if you miss a parentheses, it's hard to catch. And I think that's just one of the restrictions you're going to have to live with 36 Pro is you got to keep track of all your messy parentheses. But here it can be a little cleaner because you can have it stored in a different location. So I'll try using this method. So math 9 will take me to the integral option. I'll go from -1 to 1. But instead of typing 1 minus x squared, I'm going to call the function that's holding that 1 minus x squared, which is under vars, y vars function. And that way, I don't have to have a messy expression. And sometimes it's so long that you have to kind of scroll past and you can't see the entire expression because it's taking up more than one screen. So it's nice to have it condensed. And also, I don't need a parentheses. I can just say squared. And that's just going to take that entire expression and square it. The x, I just find it a little cleaner. Now, you can hit the math button, and that will try to convert that to a fractional value. So hit math, and then choose 1. So math 1, we'll try to convert it to a fraction. Okay. All right, any questions? All right, let's explore the problems below. And we're going to explore this. I want to change things up a little bit. Okay, we're going to try to rotate this around the y-axis. So we're going to have a different orientation. Let's practice with the other orientation here. So if you can cross out the x-axis, and we're going to do this around the y-axis. Now we're going to need a different volume formula here. Well, let's do this first. Y-axis, that's our axis of revolution. So we're going to be drawing our axis vertically. Something else is that these are not quite set up. Those vertical radius is not set up for this problem. So if you guys can just shade that in to kind of cover it up, because we have to draw our radius a little differently. Okay, so first things first, let's anchor it with our axis of revolution. We know it's going to be a y-axis. We know it's going to be vertical, so dotted line. Show the fact that I'm going to rotate. Now we're going to draw our radius, right? Our radius is always going to be perpendicular from your axis. So put your pen or pencil directly on the dotted line. That's your starting point. And we're going to extend to the boundary, which in this case, we're going to move to the right. And our radius is now going to be horizontal. So do you remember how yesterday when we're dealing with horizontal rectangles, we have a different formula, right? Everything was kind of adjusted. Our bounds were different. Our equations were different. So I'm going to put that off to the side. We can have the work for number 2 below. So here's the volume formula that's adapted for a right minus left. Oops. Okay, we still have the pi to begin with, but after you get past the integral notation, instead of x1 to x2, we're going to go from y1 to y2. We're going to find the lowest and the highest y value of the shaded region. And now, instead of r of x, now we're going to be using r of y. Our equation is going to look a little different. Okay. And as a reminder as to what needs to happen, the form that our equations for either the right or left have to take on, it has to have the form of x equals. Okay. If it doesn't take on that form, it's not quite set up for us to use that this formula. It has to have the form of x equals. So, do we need to make an adjustment with this expression, with this equation here?
Put it in terms of y.
Yeah, that's right. So x equals on the left and y is on the right. Yep. So what would this look like then if I? Yeah, you're right. Negative y plus 1 or 1 minus y. Yeah, either way. Yep, x equals, either way is fine. So I'm going to point to that, it's referring to that diagonal line. Okay. I think we have everything that we need. So let's start building our, well, let's do our radius first, big R. Okay, right minus left. So we have a horizontal radius. What's the right endpoint of the radius touching?
1 minus y.
Minus, right minus left. Left endpoint is 0. Okay, so look at the form. We have all the correct proper form necessary for either the right or the left. X equals 0. So look at those forms there. This is what we need. If it's not in this form, it's not ready for our radius equation, our radius expression. Okay, 1 minus y minus 0. That's just going to clean up to be just 1 minus y. All right, I think we have everything that we need to insert into our volume formula. So now we move on to our volume formula. Start with the pi. Definite integral from where to where? What's the lowest and highest y value of our shaded region? 0 to 1. So you can imagine we're going to stack infinite numbers of cylindrical disks, but they're all going to be stacked horizontally above each other, below and above each other. Okay. Insert our radius. Don't forget, you've got to square your radius, otherwise you're not including the area component of a circle. All right, so now we're going to practice entering in our calculator. In your calculator, you have to use x's. Don't try to use a different variable. Okay, leave pi out of your calculator. 0 to 1. Parentheses, 1 minus x, close parentheses, squared. Let's see if it'll convert to a fraction. It should. 1/3. So volume equals 1/3 what? Pi. Yeah. Units cubed. Number 2, same idea. If you guys can shade that region because that radius is not drawn the way that we're doing it for this problem. Cover it up. We're going to take this region, we're going to rotate it around the y-axis, so vertical axis of revolution. Okay, look at all these disk methods. Visually, we can instantly tell it's disk method because look at the fact that there's no gap at all between the axis and the shaded region, right? No gaps at all. It's always up against a flat surface. Okay. All right, next step. Let's draw our radius. Our radius always is going to start on the axis. Axis is going to be the center of your object. Remember, just like the radius, right? Anytime we draw the radius of a circle, we always have to include the center. So that's a reminder. We're going to start at the center, and we're going to move perpendicular to our axis. So in this case, from left to right. So again, a horizontal radius. Do we need to make some adjustments with our equation?
Set it equal to x.
Yeah, it's not quite set up right. The y equals 4 minus x squared is perfect for top minus bottom, but it's not quite set up for a right minus left. So we have to rewrite this equation here. So if I move the x squared to the left and then subtract the y over, I get x squared is equal to 4 minus y. Then we take to solve for x, square root. Now, if you take the square root, normally we have a plus or minus, but we're not showing the full parabola here. So we're not going to include the negative square root. This is only showing the positive square root. So this is only going to be x equals positive square root of 4 minus y. All right, I think we have everything that we need. Let's find our radius, big R. Okay, right minus left, right endpoint. Yep, square root of 4 minus y. Minus left endpoint is at 0. So again, look at the form, perfect match with the form that we need. They all are sitting as x equals. That's exactly what we need for anything that we want to insert into right minus left formula. Okay, so radius, that cleans up nicely to just be root 4 minus y. All right, our volume formula. Include the pi. Definite integral from lowest to highest y value.
0 to 4.
Yeah, lowest y value is 0. The highest is y equals 4. Big radius squared. Okay, now we can enter in our calculator. Well, the nice thing is that the square root and the square just cancel each other out. So you could enter it in the calculator without the square root or the square, but either way, we should get the same answer. Okay, leave the pi out. Parentheses, or actually, I don't know if I need it. Okay, I'm just going to say 4 minus x. But you can have the square root and square, but we should get the same answer. Did you guys get 8? Okay, so volume equals 8. Eight what? Pi. Yeah, it's cute, yeah. Okay, any questions? So we got our feet wet with this method. Typically, this is the easier of the method that we're going to see, but I think it's good that we're laying that foundation, understanding all the important aspects of it, and I'm also trickling in some idea of things to look for washer method. Right now, the only thing we know is that it's up against that flat surface, that there's no gap, and visually, we're going to be able to distinguish things later if we can kind of see it now. So tomorrow, I want us to do a little bit more practice with this method. Maybe we'll flip things around, flip between right minus left and top minus bottom, see if we can understand it, know how to look for the intersections, know how to write our equations or rewrite our equations, and then we didn't do the back page of the area worksheet, so maybe we can pick out some problems that we didn't get to, just kind of go back and forth. So tomorrow will just be kind of a review day, with this method and area, and then we'll pick up our next section with washer method on Thursday. Okay. All right, thanks everyone. Hope you guys have a great day. See you guys tomorrow.